The name of this video is Finite Dielectric Cylinder. In fact, in this video, we are going to consider the first example on how to solve problems involving dielectric materials. In this case, we are going to consider a simple cylindrical dielectric material. So it's a cylinder with finite length, capital L, and two areas on the sides with the area pi r square, capital R square, where capital R is the radius of the two bases. So it's a finite cylinder which we polarize. Now, before entering into the details of such a problem, let me quickly give you a summary of how all these problems work and how we're going to tackle the general problem of solving dielectric materials. So the way it works is that, first of all, we have a dielectric material which is unpolarized, so it's uncharged and unpolarized. So then we switch on an external electric field E naught, which can be uniform or not. So this is our external electric field. So that's the first thing you need to do. In order to polarize a dielectric material, you switch an E naught on. As a consequence, this generates a polarization P. To be noted that this polarization P, capital P vector, in most of the cases we are going to study in this course, actually in all the cases we are going to study in this course, is directly proportional to E naught by means of a constant. We will come back to this later. So P and E naught are proportional to each other. So the direction of P is the same as that of E naught, as we kind of seen already when we discussed the molecular model of the electric material. It doesn't have to be. Okay, it could be a tensor relationship, but for our purposes, they are going to be directed in the same direction. So as a consequence, P generates, as we know, a polarization, that is polarization charges in particular, a polarization charge sigma P on the surface of the dielectric materials with density sigma P locally, and rho P in the volume, which we know they are given by P dot n and minus the divergence of capital P respectively. So we know how to compute those. These charges, obviously, they generate another electric field, which we call EP. This, some people call it the polarization field, other people call it the depolarization field. I think it's actually better, it would be ED, but let's call it EP because that's a general notation. Why is it's basically a reaction or a depolarizing field. So it's similar to, so what's happening in this dielectric material is similar to what happens in conductors, which we have seen in FIS 242. So in conductors, when I have a conductor in vacuum, I switch on an external field E naught. Charge-free carriers begin to move, to migrate in opposite direction compared to the field lines of E naught. Therefore, there will be a new balance of charges. Okay, so let me do a quick sketch about that here. So we remind ourselves what's happening here. It's the same thing. So if this is one surface and this is the other surface of a conductor or a dielectric material, it doesn't really matter for the purposes of what we're doing now here. So this is our, is a cross-section here, and this is another section here. So this is our dielectric material or conductor. And I will tell you in a minute what is the key difference between whether this is a conductor or a dielectric material, okay, macroscopically. So I switch on my E naught. So E naught is my external field here, which resides both outside and inside the material itself. So then, as I said, negative charges begin to migrate and accumulate on the left-hand side of the dielectric material or conductor. Similarly, there will be positive charges left on the right-hand side. So this, as a consequence, generates a reaction field E, which in the case of conducting materials, we call it ER, reaction. In this case, we call it EP, the polarization or depolarizing field, okay? So it's depolarizing because it's opposite with respect to E naught, which is what generates P. Because P, of course, as I just said, is going to reside only within the electric material and is going to be directed as E naught. This is my P polarization vector. Now, the key difference between conductors and dielectric materials is that in conductors, the EP is exactly macroscopic electrostatic equilibrium conditions minus E naught. That is, inside the conductor, there is no electric field. Whereas in the case of the electric materials, the overall field which I obtain by linearly superimposing, so the E total given by E naught plus linearly superimposed with EP inside the material is generally different than 0, okay? At any point inside this material. Whereas in conductors in ME, it was equal to 0. That is, in conductors, these charges perform a full screening. That is, a perfect conductor screens out completely, shields out, is a good shield of the electric field inode. There is no field inside. So inside we don't even know that there is any inode. That's why we can do electrostatic shields, electric shields by means of conductors. In the case of the electric materials, that's not the case. This screening, these positive and negative charges, which are opposite with respect to the field lines of inode, only partially screen the field inode. Therefore, there is a finite field inside the dielectric material. That's the key difference between conductors and dielectric materials in this at this macroscopic stage. All right. So now in this part, in the first set of problems we're going to study here, what we want to find is EP given P. So I will not show what is the relationship between E naught that generates P. This step, we will come back to this at the end of these videos about dielectric materials. Now, somebody gives me P, typically uniform. So somebody gives me P, is given. And what is, given P, the EP due to that P? So that's what we are doing. At the end, we will perform a self-consistent method where we are going to linearly superimpose P and E naught to find the total E. And we will see what is the relationship between P and total E and eventually E naught. So it's a little bit convoluted, but that's the most pedagogical approach. So for now, somebody gives me capital P. We don't know how that was generated, and I want to use it only to calculate the reaction field, EP, the polarization field or depolarizing field. At the end, we're going to sum them up to see self-consistently what's happening in this device. Now, the interesting thing is that, of course, there are transients, like in conductors, right? So as soon as I switch E naught, there is a migration, these charges start to stretch, to move around, there is a torque, there is dynamics. So this self-consistent method, which we are starting now, and we will end up at the end, we will finish at the end of these lectures on dielectric materials, basically is a very cool method because it allows us to bypass all the knowledge of transients, which would be super complicated to study in detail microscopically. So we know that there is a transient, it's very quick, but this method allows us to bypass all the complicated physics, which we would need to solve in that case. All right, so now let me also remind you that briefly that P, so let's remind ourselves what is capital P. Capital P microscopic definition is rho plus times L, the displacement vector. So that's what it is, because times the volume, it would be small p. This we know that is actually dP divided by dV calculated at Q, which means we can, by integration, we can find that the integral over the region where the dielectric material is defined of dP, which is equal to small p, this has to be equal to the integral in the region capital omega of capital P dV, okay? So if it so happens that P is uniform, well, in that case, if P is uniform, this is a subcase, let me do it down here. If capital P is uniform, well, then in that case, small p is equal to capital P vector, the polarization vector, times the volume. So it's a very simple dipole with dipole moment, small p equal the polarization vector times V. Only when capital P is uniform. Uniform is what we are going to study in most of these problems. So in fact, it's very useful to know that. All right. So now that we know all that, let's delve into the details of the problem we want to investigate here, which is exactly that of a finite dielectric cylinder. Okay. So in fact, this is the most complicated part because we cannot really solve it analytically because it's finite, so there are fringing effects and edge effects. And so I will just give you a sort of qualitative idea, but it's useful then to to use it to further develop it to find the degenerate cases, which are more useful, like the infinite slab. We'll come back to that later on. So let me sketch down here in 3D first, and here I will do the eventually in 2D, my finite dielectric material, cylindrical. So it looks like this. So this is one base of the dielectric material, where this is the radius capital R. This dielectric material is characterized by a certain length, capital L, and this is the other base. and this is the side which we don't get to see. All right, so the overall length of this material is capital L, and R is the radius. So these bases here, they are characterized by an area A, which happens to be, this is the right face, this is the left base. In both cases is equal to pi capital R squared, finite. We assume that we have uniform polarization P. And this P is uniform. Along the central axis of this cylinder, where we can sketch the x-axis or z-axis, since we are in cylindrical coordinate system, let's call it z, the z-axis, and the origin, let's say, is here in the center. This is the r-axis of a cylindrical coordinate system, the origin O r bar phi z. And bar phi, I'm not going to show it in this case, but there is such a thing, okay? So it's a cylindrical coordinate system. Great. The surfaces, of course, so this surface here is what we call capital sigma left, with area A left equal to A right, and in fact this other surface is capital sigma right, R, subscript R. Great. The lateral surface of this cylinder, we call it, the lateral surface is capital sigma lateral, LAT. Perfect. So now the normal unit vector here on the left-hand side, we call it NL, which with respect to z happens to be equal to minus UZ, unit vector along the z direction. Similarly, on the other side here, we have N right, which in this case happens to be equal to UZ. I'm not going to write that for space reasons. The lateral, if this is a point on the lateral surface of the cylinder, this is N lateral, is the unit vector on the side of the cylinder, which happens to form a 90-degree angle with the polarization vector P, which is directly normal to N lateral. Everywhere is uniform, so this is my P at this point here. Okay, great. Okay, so with respect to this coordinate system, capital P vector, the polarization vector, is equal to the norm of capital P vector times UZ. Is uniform and directed along the z-axis, and that does not depend on r, bar phi, or z. It does not, because it's uniform. Okay. So given all this notation here, now the first question I want to ask is, what are the charges? So what is the polarization charge? Let's say, so of course, as always, we call this volume here capital omega, which is the body of the cylinder, okay? There is vacuum outside. Okay, so what is the polarization charge, rho p, associated with this cylinder? Well, is minus the divergence of capital P. What happens if capital P is a uniform polarization vector? Stop for a minute, think about it, and come back. Okay, now, so if you came back, you should have realized that if P is uniform, the divergence of P clearly is 0. So every time we have a uniform P field, which is the polarization field of vector P, rho P is 0. Great. That is not the case for the sigmas associated with this object. In fact, sigma associated with the left surface is given by the norm of capital P vector in this coordinate system times UZ dotted with N left, which is minus UZ. Minus because N left is minus UZ. So UZ dot UZ with the minus is minus 1, so it's minus the norm of P vector. So clearly this quantity is negative. And we will see in a minute that it makes qualitative sense. Now in Piazza I want you to find sigma right, okay, which is straightforward. As soon as I gave you sigma left, you should be able to find that readily. What about the surface charge sigma lateral? Well, in this case, we're going to have P vector dotted and lateral, which as shown here, they form a 90-degree angle. And so this is identically equal to 0. So there is no lateral charge. Okay. Now, let us make a sketch. So also this means that the entire area here on the left is going to be charged with a negative charge. The total negative charge associated with this region is Q left, which is the area of that region, pi r squared times sigma left. So it's minus the norm of P times pi capital R squared. And similarly, you can compute the charge on the right. And now if you've done it, go to Piazza, you should show me the details there, but clearly it has to be positively charged. So we're going to have a positive charge density here, which is going to be Q right, and it's going to be positive. So it's going to be exactly the same, but with the positive sign. All right. So now let's make this sketch instead of 3D, let's make it in 2D. So I will do a two-dimensional cross-section of these objects. I'm going to look at it from the side. So these discs, I just see a straight line. Okay, so it's side view of this cylinder. So the side view, I need to leave some space to make sure that everything will fit in. Let's put it here. This is the side view of the cylinder, where this is the right hand side, so the right surface base, and this one is the left base. Okay? Okay, so now as always, let's sketch our coordinate system, where this is the z-axis, this is the origin here, so this is the r-axis, and I will leave it like this. Intuitively, qualitatively, does it make sense that sigma left is negative? Well, we have a polarization field P directed towards the right, okay, which means this was generated by an E naught also directed towards the right, which means if E naught and P point towards the right, clearly negative charges will accumulate here on the left hand side of this cylinder. They will be stretched by a certain L vector, which is the displacement vector. And on the other side of the L vector, we have the positive charges. So clearly, the same thing happens on the other side here. So we're going to have positive charge, positive charge. My displacement vector L, always from negative to positive by definition. So clearly, we are having an effective negative charge here on the left surface and an effective positive charge here on the right surface. So it makes totally sense that this one is negative, and if you calculate it in Piazza, the other one is just plus the norm of P pi r squared. So it makes sense. You always need to go back to the intuition of the dipoles, because that's how this whole thing actually works. Okay? So the molecules get stretched because of E naught, and as a consequence, capital P, which is the only thing I'm given. And they align with these field lines where negative charge, of course, are opposite with respect to the direction of P, which is the same as the direction of E naught, the external field or polarizing field. All right. So now that we have all that in place, I want to ask you another question in Piazza. And the question in Piazza, in fact, is as follows. So the question in Piazza which I have for you is a refresher from 242. So in this case, because of the rotational symmetry about the z-axis and the irrotational property of the electric field E, I want that you show that there cannot be an E phi, EP phi. EP is what we want to calculate the polarization field associated with this object. This has to be 0. Please show it and tell me how you would do that in Piazza, okay? These are the two properties you need to do that. We have done this very much in detail in 242. So it's a good refresher to do that, all right? So this is true for each point capital P in space. Now, what if I want to sketch the field lines of EP? Okay, so outside this object, so what do we see here? We see a little cylinder with a negative charge on this face, QL minus norm of P pi r square, and a positive charge, which is the opposite of this sign, Q right, on the other side here. So there is a negative charge here, and a positive charge here. What do you think will look like the electric field EP? So I have a P, which generates this polarization of molecules, and now these polarized molecules react to this P, generating an electric field EP, the polarization field, or depolarizing field. Outside, this is like a dipole, okay? So like a dipole with a negative and a positive charge, so the field lines outside will be, particularly if you go far away, of course, if this is a small object compared to the entire universe, it's very much like an electric dipole. Okay, so let's sketch our field lines. So the field lines, let's do them in green, not to confuse them with all the other, with the negative and positive charges here. So actually, let's do them in blue. So in this case, of course, there will be a field line here. So this is the negative charge. So obviously, this field line, if I have a test charge positive, will be attracted by this negative charge. And so the field line here looks like that. Similarly here, the field line will point towards the outside. Okay, so if I have negative charges, this is my test charge here. So obviously it gets attracted by these negative charges here. Okay, they're opposite. Whereas here, it gets repulsed. Here, for example, if I look at some other position, I will have a field which looks like that. Outside is symmetric. So if I look at this point here, let me just make a quick line, which is useful for some reasons which will become apparent in a minute. So this is a field outside. And if I go further, there will be, for example, a field like this. Okay, great. Now this is symmetric, so the same thing will happen below, and I'm not going to sketch it because it's symmetric. Okay, rotation symmetry about the z-axis, so I can only sketch. It's enough, it's sufficient to sketch the field lines above. All right. Good. So now that we have all that in place, so it's like an electric dipole outside. It behaves like an electric dipole outside. Okay. So outside is approximately an electric dipole. Okay, we know that. What about inside? What happens now to the field inside? Clearly, this is a reaction field inside the P, which has to point from the positive to the negative charges. So it's opposite compared to P, and I remind you that P points in this direction. Same as E naught, and E naught, we will come back to that again at the end of this series of videos. So as expected, the polarization field or depolarizing field is depolarizing because it is opposing, is a reaction field compared to the field outside, for example, in this case. So how do we sketch these field lines? Well, let's look at the boundary condition here. So if I look at this surface on the left, and the same applies for the right, and I will let you do the right on your own. So in this case, if I pick a point here, any point on the left surface, the normal components of the field, in this case, the normal components are the EZ components, or if you want EPZ, to be precise. Whereas the tangent components are EPR. Obviously, the radial components are tangent, whereas the Z components are normal in this surface, similar to R. So if this is the case here, so what happens from 242, we should know that this means for the normal components, if we define this region here as region 2, and the vacuum outside as region 1, so n points from 2 to 1, n to 1, using an n which goes from 2 to 1, we know that EPZ1 minus EPZ2, which are the normal components with respect to this n to 1, okay, they have to be equal to whatever sigma we have on that surface, which is sigma L divided by epsilon naught. Sigma L is a negative quantity, so they are discontinuous. The Z components are discontinuous. This makes very much sense because we know that outside the field points in this direction, whereas inside is the opposite direction, so clearly are discontinuous. Whereas the tangent components from 242, we know that they must be continuous. So EPR1 minus EPR2, they have to be equal to 0, so they are continuous, okay? So one possible configuration to make sure that the radial components are continuous, that they are 0, and so typically this happens in this fashion, so which means on the other side, we continue with the minimum here, so there is 0 tangent components. Okay, so then this field typically goes up, and it goes like this, and here similarly, it goes like that. Okay, actually, it's not always necessary that the second one, let me do it within for generality, so we see all possible cases. Okay. So this one is closer to the surface, so it may go outside. This one we keep it within. It has to be symmetric, so we'll go up here, and then it will behave symmetrically on the other side. So clearly, we will end up doing something similar here, and something similar here. So these are the field lines. Of course, in this case, we need to be particularly careful, because inside, the field lines are opposite, because this is the reaction field. So it's good that I made a mistake. So it's clear that now you will definitely remember that inside the field lines go from plus to minus, so they point in this direction. And the simpler one, of course, is here, pointing in this direction, then they are symmetric below. Clearly on the lateral surface, so if I look now at the lateral surface, in that case, the normal components are the EPR components, whereas the tangent components are the EPZ components. They swap the role, of course, because now we are looking at the point here on the lateral surface, let's say this point here, these points. Okay, in this case, in both cases, since we do not have a lateral surface charge, sigma lateral is 0, both components must be continuous, which means that EP_R1 has to be equal to EP_R2. In this case, these are the normal components. They're 0 because sigma lateral is 0. And similarly, EP_Z1 has to be equal to EP_Z2, and this, of course, is always true because it's the rotational property of the electric field from 242. Gauss theorem rotational property, Gauss theorem in this case, sigma lateral is 0, so of course they have to be continuous. And this makes sense, and that's why here I've done them continuously in this fashion. And of course inside also are continuous. Okay, so this gives you sort of an idea how the field looks like for this object. Perhaps let me ask you a question in Piazza. So given the fact that this condition is true, and this condition is true, given these boundary conditions, do you think there could be other options, other possible configuration for the E field here? At, let's say, L or right? So this is the question, okay? So in other words, is this smooth approach where the R components, which are the tangent in this case, are 0, and so I have this minimum like this, is this the only option, or I can have something different? Could I have something like this, for example? That's a question, okay? So that's what I want you to discuss a little bit in Piazza. And again, this is because in real life, in order to solve this problem, you want to make really a simulation of this finite cylinder, okay? It's much easier to perform a simulation. However, just with these boundary conditions, I can already discover quite a bit about the field lines, and that's why we can do that, which is actually very important, because always doing a back of the envelope sketch of the field lines before performing a simulation gives you a clear idea of what you expect from the simulation. So it's useful to do this exercise in this fashion. So to summarize this video, finite dielectric cylinder. First, I give you a preamble of how this whole thing works. I give you a dielectric material, I switch on an external E0, which generates in the same direction, in all our cases a P vector, which is what I'm giving you now. And I'm giving you a P uniform, typically in these examples. This P generates rho P, in this case rho P is 0, because the divergence of P is 0, P is uniform inside, so there is only a sigma P on the surfaces, on the lateral surfaces, positive and negative, which makes sense with the intuition of the dipoles. So we know that these are molecules which get stretched and polarized in this fashion. So this makes totally sense, and we calculated it. Minus norm of P, pi r square is the charge here, and the opposite, which is positive, on the other side. So clearly now, the key thing to remember is that these plus and minus charges generate a polarization field. So this is what we call EP, all these blue field lines here, inside and outside. Outside is that of a dipole, an electric dipole, whereas inside it's opposed compared to P because it reacts. In the case of conductors, this reaction is 100%, which means I expel completely any field from inside. Here is not. So I still have, even when later we're going to superimpose this with E0, the field inside is not going to be 0. So electric dipole inside, that this plus minus, a sort of capacitor kind of thing, double layer of charge, but with a little bit more complicated lines because it's finite. In this case, and to guess a little bit the shape of the field lines, we use these boundary conditions, and I ask a few questions about that. In the next series of videos, we're going to degenerate this cylinder to make it infinitely large or infinitely long in this direction. So either along Z or along R. That's it.